Our project centers around amyloid aggregation. This is a process wherein soluble proteins undergo a conformational change and aggregate into a characteristic fibrillar structure with beta sheets stacked perpendicular to the long axis of the fibril. Many proteins are considered amyloids, with the most famous example being amyloid beta, the protein that aggregates into the characteristic plaques found in the brains of patients with Alzheimer's disease. Because amyloids are implicated in many diseases, investigating and inhibiting the mechanisms of amyloid aggregation is a rich research area. In my research, I am studying cobalt-based inhibitors of amyloid aggregation, developed by the Mead Group. The overall goal of our project for this class is to understand the mechanism of amyloid inhibition by the cobalt complex using modeling. The necessary data is obtained by performing in vitro amyloid aggregations. After resuspending monomerized A-beta, I use a small fluorescent dye called thioflavin T to monitor the increase in beta sheet character that develops as the protein aggregates. Initially, the protein is disordered, and there is no fluorescence. As aggregation occurs, the monomers begin to combine into small aggregates, termed oligomers. This process is relatively slow, and so is termed the lag phase of the aggregation. The oligomers form seeds for further aggregation, and once enough nuclei have been formed, aggregation proceeds at a much faster rate, as the monomers polymerize into larger fibrils. As fibrils form, they act as nuclei for the production of more fibrils, resulting in exponential growth. This fast growth of fibrils is termed the elongation phase. As the oligomers grow into larger aggregates, thioflavin T is able to bind. Binding of thioflavin T sterically hinders its rotation, resulting in an increase in fluorescence. Eventually, an equilibrium is reached between fibrils, oligomers, and monomers.
Studies have revealed two main pathways through which proteins aggregate. The first pathway is termed the primary pathway, in which the rate of aggregation is controlled by the rate at which individual monomers combine to form nuclei capable of entering the elongation phase. In the second pathway, the rate of aggregation is primarily set by the concentration of existing fibrils. In real systems, it has been shown that both primary and secondary pathways are active during protein aggregation. Accordingly, we can see that the proposed inhibitor has more than one possible point of attack. To that end, we looked to identify specific variables related to the different pathways. The first variable, gamma, is the slope of the linear relationship between the lag time and the initial concentration of monomer. Lag time is defined as the point along a typical aggregation reaction, shown in the left image, where the line tangent to the maximum rate of the reaction intersects with the x-axis, or the length of the lag phase. The variable gamma represents how strongly this initial slow growth phase is dependent on free monomer. The parameter gamma is directly dependent on how many monomers are needed to form these nuclei in the two different pathways. The term for the number of molecules involved in primary nucleation is termed NC. The number of molecules that form a nuclei when an existing fibril catalyzes the reaction, i.e. secondary nucleation, is termed N2. Another way to look at these nucleation terms, NC and N2, is that they give the reaction order, or give some idea of how rate-limiting a reactant is in a typical equation. Lambda and kappa are rate constants. Lambda is the rate at which fibrils form when the lag time is primarily determined by the concentration of free monomers. Kappa describes the rate of fibril formation when the system is instead primarily dependent on the concentration of existing fibrils. To this end, we found a theoretical model that describes aggregation as a function of these variables, NC, N2, lambda, and kappa. published by the Knowles Group at Cambridge in 2009, shown here. In this model, m of t, the current mass of aggregate, normalized over m of infinity, or the maximum possible mass of aggregate, grows as time proceeds, reflecting aggregation. In this model, there are several power law relationships as well as exponential terms, making for a nonlinear dependence on time, seen in typical aggregation experimental data. Now that we have a theoretical framework for this aggregation process, we wanted to explore how this novel inhibitor might affect aggregation by fitting experimental data to this master equation. If we find that certain parameters capture the effects of inhibition more reliably than others, this would give us some insight into what steps in this process are being targeted by the inhibitor.
Okay, now we will describe the experimental setup that we used. We considered first 5 different initial monomer concentrations, shown here. We then considered for each one of these initial monomer concentrations 3 different inhibitor levels, the 0 equivalents, 0.05 equivalents, and 0.1 equivalents. Now, for each one of these 15 experimental setups, we performed 3 different trials, giving us a total of 45 data sets that we'll consider. Now, once we have this raw data, we need to normalize our data in order to compare to our analytical model. So the first thing we do is subtract out what's called the negative control, which is the reading of the background fluorescence. Once we've done that, we then consider each one of our individual 45 trials. We average over the steady state, or the final monomer concentration for each one of those trials. We consider that to be the last 5 data points for each trial. We then normalize that given trial to its steady state average. Once we've done that, we then consider our 15 different experimental setups. And for each of those 15, we find the mean and the standard deviation of the 3 associated normalized trials. The results are shown here. This is for the untreated data, so there is no inhibitor present, and we see our 5 different monomer concentrations. We can put our error bars from the standard deviation to see that we do in fact have some fairly noisy data. We move on to the next level of inhibitor at 0.05 equivalents, and the error bars with that showing that in this case the blue curve especially has some very, very noisy data. And finally, for the 0.1 equivalents and its error bars. Once we have this data, we then want to try to compute gamma. Unfortunately, this preliminary data is too noisy to actually compute the lag time. However, we found that we can use what's known as the half time as a proxy for the lag time. The half time is defined as the time at which the normalized data crosses the threshold 1/2. Unfortunately, though, our preliminary data is so noisy that even computing the half-time accurately is difficult. As we see, once we have attempted to compute gamma, we found here, for example, in the untreated case, that gamma was minus 0.17, roughly. We notice that this is greater than the value of negative 0.5, which is the largest value that gamma can take. So what we see is that our calculation of the half-time was probably too inaccurate, and our data was too noisy to be able to reliably get a value for gamma. What that means, though, is that we're now unable to infer the values of NC and N2 from just the scaling laws between the lag time and the monomer concentration. So instead, we'll have to try to find them through our curve fitting. So let's look at our curve fitting procedure. For each one of our 15 average normalized data sets corresponding to one of our 15 experimental setups, we will loop over a range of possible integer values for NC and N2. For each pair of NC into values that we look at, we will then fit that analytic model that we showed for the values of lambda and kappa and record the R2 value of the fit. We can then keep track of the best fit we've seen so far and record the NC into kappa and lambda values that gave that best fit. So at the end, we will have, for each one of the 15 normalized data sets, we will have values for NC into kappa and lambda that gave the best fit.
We start with the untreated case because based on known results from the Knowles group for the aggregation of A beta 42, we should expect that NC equals 2 in the untreated case. The fit from those parameters is the predicted fit curve. The best fit curve is made from allowing NC and N2 to vary between 1 and 15. For all concentrations in the untreated case, NC equals N2 equals 2 did not give the best fit since our data is not particularly robust, especially for the lower concentration runs. But for the higher concentration runs, the predicted fit is close to the best fit. If our preliminary data was more robust, we would have been able to use the kappa and lambda values found via fitting at different concentrations to report statistics for monomer concentration independent primary and secondary pathway rates. But we didn't think our preliminary data merited that analysis at this point. Again, if we had more robust data, our next step would have been to produce the gamma scaling plots for the cases that were treated with the inhibitor. This would have allowed us to infer whether the inhibitor affected the reaction orders in C and N2 from the behavior of gamma. However, as you can see, our preliminary measurements for gamma were not reliable in the treated cases either. In fact, for the highest dose of the inhibitor, we initially got a positive gamma value, which is completely unphysical. Even when we removed one monomer concentration group that appeared to be an outlier, the gamma values were still off, though they were all at least negative. In any case, we still performed the same curve fitting procedure as before and were able to report a best fit and a predicted fit given by NC equals N2 equals 2 for each monomer concentration and inhibitor dose. Here are the results for the inhibited cases at the highest monomer concentration. In both cases, the predicted fit is fairly good, and if we had as good of fits across monomer concentration runs, we could again have reported monomer independent rate statistics for kappa and gamma to try to draw conclusions about the effect of the inhibitor on the rates by comparing with the untreated case. Since we are unable to reliably report results due to the quality of our preliminary data, we would like to perform further experiments in the future with an enhanced experimental protocol where we would do more runs with higher monomer concentrations and perform more observations so that we can get better resolution of the aggregation period. With better data, we could use our analysis and fitting procedure to produce results and draw conclusions about how the cobalt inhibitor affected the reaction orders and rates. And here are references. Thank you for your attention.